Hello, I'm the principal investigator, Jacob Young, and this tech talk is over a fast solid-state pulse power modulator. All right, so first off, a little bit about SARA. We have two different divisions. One is out on the West Coast in California, and a second is in Colorado Springs, Colorado. And that is the High Power Electromagnetics Division, and that's where the effort that we will be talking about today is taking place. So here we have a long history of developing various pulse power technologies. At the top on the left, you can see a short list of various pulsars that we have developed over the years. One of the more notable ones is the Marx generator that's pointed out kind of in the middle on the right side of your page. And this is an ultra compact design with the enabling technology being the in-house capacitors that are designed and manufactured here at SARA. So this allows the capacitors to be packaged in application-specific form factors, optimizing the volume available. Another technology that is unique to SARA is our solid-state switch packaging. So both that as well as the capacitors just mentioned are two of the critical components in the project that is being discussed here today. So a few other things that SARA works on that are worth mentioning are custom power supplies, and that's for a variety of applications, as you can see there, as well as antenna design, and that's anywhere from low power antennas all the way up to megawatt and gigawatt class antennas for HPM applications. And then finally, we work on high power microwave and directed energy sources, such as the Vercator, as you can see in the bottom right there. So the focus of this SBIR is to develop a next generation pulse power modulator. So traditional spark gap switched HPM drivers have a number of limitations, those of which are listed in red. The first being low repetition rate, which is just due to them being gas type switch systems. The second is short lifetime, resulting in those systems needing frequent maintenance. And the final limitation is the very limited waveform shaping capabilities. So for example, on a Marx generator, the output is typically defined by the equivalent R, L, and C of the circuit. And if you do want some pulse shaping, that would require an additional stage, increasing the complexity, cost, and volume of the solution. Here at SARA, we're working on developing an HPM driver that takes advantage of a few different things. The first of which being SARA's ability to make custom solid-state switch packages, or modules as we usually call them. This allows for the high voltage and high current handling capability. And the solid-state nature of the system enables both high repetition rates and very low jitter. We're also leveraging an advanced modulator topology, which I'll talk a little bit more about on the next slide. And then on the right, you can see the proposed threshold as well as target parameters that we're aiming for in the final system. The modulator topology that we ultimately determined was best to meet those requirements was a solid-state linear transformer driver, or LTD, as it's more commonly referred to. This has a few advantages compared to the traditional solutions that are spark gap switched. The first of which being that the voltage is modular. So if I just increase the number of stages of the system, I can increase the output voltage proportionally. And when I say stages, if we look at the image on the right, a stage is just one layer of that stack. Another advantage is that the current is also modular. So if I increase the number of bricks per stage, then I can increase the current handling capability. And due to the solid state nature of the system, this would allow for arbitrary waveform generation, as well as very low jitter and high repetition rates, as was previously mentioned. As of Q3 in 2023, we did show the demonstration of a single stage, so that being 6.5 kV output voltage, as well as less than 10 nanosecond rise times. And this also was able to do greater than 2 Ka peak current. So at the moment, we're working on developing a small scaled down demonstrator, that being a 3-stage system. And then once that is proven, we'll work towards expanding that, most likely to an H-stage system after that. Here you can see a schedule of our milestones as well as their respective status all the way to the right. And as you'll notice, most objectives have been completed at this point in time. The next objective that we are working towards is finalizing both the mechanical and electrical design of the system to ensure that those two aspects work in concert with one another. And we're doing this through the scaled down 3-stage system. From there, we'll work on expanding the LTD up to most likely 8 stages within this phase 2 effort, and then hopefully beyond that, 16 stages for the final system. So here are just a few of the key features and benefits of the solid-state LTD that SARA is developing. The first of which is that we're using wide bandgap semiconductor devices. So this is really going to allow us to minimize the overall modulator size and volume. The other two benefits, ones that I've already mentioned, are the high repetition rate as well as the very low jitter. So this is extremely important in certain systems such as phased antenna arrays. The next advantage is that we are using an advanced modulator architecture. So with an LTD, each stage is ground referenced, meaning at most you typically only need to hold off 6.5 kV, and this is going to reduce size, weight, and maintenance of the final system. Another benefit here is just the arbitrary waveform generation. This gives you some control over the final output of your system and gives you another knob to tailor that profile with. The third and final advantage that I'm going to mention here is just what SARA brings to the table when building this system. So we are able to integrate a lot of custom components, those being the film capacitors we design in-house, as well as the custom solid-state switch packaging. This reduces supply chain risk and also enables extremely customizable solutions that optimize the size, weight, and power versus cost of the system. The LTD that SARA is developing would fit into a number of DoD and DOE applications. So on the DoD side, it would fit into nearly any HPM system as the pulsed power driver that drives the high-powered microwave source. A number of those can be seen down below. On the DOE side, it would be excellent for induction accelerators for radiography. So one example of that being Project Scorpius out in Nevada. It would also fit into a number of commercial applications, so those being pulsed electric field treatment, ion implantation, as well as carbon ion therapy. Ultimately, SARA is looking to partner with DoD programs and prime contractors to further develop this technology as a subcomponent to a larger system. From there, it could then be fully integrated into an HPM system as the pulsed power driver. Later down the line, SARA would then have the capabilities to do system testing and characterization, such as lethality and survivability, all on site here at SARA. Ultimately, SARA specializes in development of novel technologies and custom solutions, and we're equipped for low-rate initial production and full-rate production. If anyone has any questions about the technology, feel free to reach out to myself. Again, I'm Jacob Young, or the other two contacts listed here. Thank you for your time.